Hello again, guys. Today, we'll discuss the quantum mechanical model of the atom and who are the people behind this model. Sorry guys if the video looks like it's beating. I don't know. I think it is the focus of the camera. That is why it's like thumping. And I don't know how to adjust this. So let's bear with this. So it's just a little beating. The video is just a little beating. Okay. In the chapters 5.1 to 5.3, we discussed that light in the form of energy, so it has wavelength and frequency. So that is why there is a wave property for this light or for the radiation. And also, some scientists argue that there are particle properties of light, since Max Planck described that this light or this electromagnetic radiations has the capability of absorbing energy or emitting energy in the form of quantum or quanta. By having these thoughts, Louis de Broglie posed this question: if light can be viewed in terms of both wave and particle properties, so meaning it has the wave properties such as wavelength and frequency, and also the particle properties such as we can know its location, as well as we can have the mass as well as its energy. Why can particles of matter such as electrons be treated the same way? In his question, since the radiation is viewed more in the wave property and then it has the particle property, this time he looks at matter which has physical properties and then determine its wave nature. So he proposed that the particles such as electrons or even us humans are having large macro scale properties, we also have wave properties. And he has this equation, the de Broglie equation, in which he calculated the wavelength lambda, which is proportional with the h or Planck's constant and inversely proportional with the momentum. So momentum is mv, that is the mass times the volume. Looking at this equation, we have the wavelength. If we have a wavelength, then there is a corresponding mass. So that means this wave property, wavelength, is convertible into a particle property. And at the same time, so if we look at ourselves, for example, our electrons, which has definitely a mass, so we are particles or we are made up of particles, then we can calculate for our wavelength. So this de Broglie wavelength equation was widely accepted since it did not violate any of the laws or theories done by the previous scientists. But at the same time, this questioned the whole scientific community whether we as humans can definitely have wavelength or wave properties. So after this suggestion by de Broglie, which we call this suggestion as the duality of nature, Sir Heisenberg proposed uncertainty principle. So this uncertainty principle states that it is impossible to simultaneously determine the exact position and the exact momentum of an electron. So this is done by calculations, and this specific and very intricate calculations lead this determination that if we need to determine the exact position, then we cannot determine the momentum or the mass and the volume of a particular particle. Or if we need to determine its momentum, then we cannot determine the exact position. So this momentum is very much uh, needed in the study of physics and chemistry, since this momentum from the previous slide is proportional or is inversely proportional with the wavelength, and the wavelength is inversely proportional with the energy. If you recall, the equation E is equal to hc over lambda. So that means that this E, or the energy, is directly proportional with the momentum. So if we need or if we will state this uncertainty principle more elaborately or more in the physical way, so Heisenberg proposed this uncertainty principle, which states that you cannot determine simultaneously the exact position and the exact energy of any particles. Or we have wave. Okay, so if we have the atom in which it has electrons moving fast around its nucleus, how can we now visualize the atom? So we have the Dalton's theory, wherein we have the electrons and the positive charges. Then we have the Rutherfords, in which there is a nucleus. So how about the electrons? Where can we locate, or where can we find them? Okay, so this one, Schrödinger, so he made a wave equation. So take note, this is a wave equation. So this equation has the solutions called wave functions. So still the equations contain the answers as still equations that describe the behavior of the electron. Take note, the behavior in a hydrogen atom. So it's not very complicated in a hydrogen atom, since we only have one electron moving around the nucleus. So this behavior corresponds to, first, the location, and second, for the momentum or energy of the electron. So this means that in this wave equation, we can find this location and the momentum of the electron, but at the same time, we cannot really locate the two. So meaning to say, we have to choose what we will determine, the exact location or the exact energy or exact momentum. In these wave functions in chemistry and in physics, it is more dwelled into finding the exact energy and not the location. Since the electrons move fast or move quickly, the location is not very much feasible to find, as well as in a split second or in a split nanosecond, there is a change in the location of the electron, but the energy will remain the same. Okay, so this wave function, if we square this, so this is related to the electron density. So when we say electron density, that is the probability of finding the electron in a given region of space. So for example, we have the nucleus in this off, for example, and then the electron density, so the or we call this as the electron cloud surrounding this nucleus. So we can get that electron density or the probability of finding that electron in that given of space by making the wave function equal to its square. Okay, so how do we visualize now an atom if we just have a function or a wave function in which it predicts the probability where we can find the electron. Okay, so for the solutions of squaring these wave functions, if we plot the points, just like in mathematics, we get this figure. So this figure has the points. So there are many points in the closer region of space intersecting x, y, and z axis. So we call this as the electron density distribution. So this means that more likely we would find the electrons inside this region of space. And if we will just look at the boundary surface, or the surface in which most of the time 99% of the electron will be seen. So we have this figure. So this is a spherical shape. So this means that in those sphere, we can find 99% of the time the electron. So this does not mean that the electron is found in one point or in one location, but most of the time it is found revolving inside this region of space. So we call this figures as the atomic orbital. So we have the orbital. So it does not mean that the atom revolves around it, but the electrons revolving around the nucleus, which comprises the whole atom. So this atomic orbital is also called the quantum mechanical model of the atom. We have different atomic orbitals. So that means some of the electrons assume this spherical shape where we can find, or we can also have different spatial three-dimensional figures. Just like this. Okay, for if we have s atomic orbitals, so later on we'll discuss this s, this p, and d orbitals. For s atomic orbitals, we see that there are spherical shape. So if we have 1s, it is very small. For 2s, so it's just a medium sphere. For 3s, we have larger sphere. For p atomic orbitals, then we have this two oblongated figures, wherein if we have the, for example, this 3px and 2px, so they are located in the x-axis. So if we have 2py or 3py, so these are located on the y-axis. And the same goes with the 3pz and 2pz. For d atomic orbitals, we have a much more intricate oblongated figures. So we have 3D z squared, 3D xz, 3D yz, 3D xy, and 3D x squared minus y squared. So don't worry, I will not make this I will not make you memorize this orbitals. You just have to know how the orbitals look like, as well as how does these atomic orbitals become like this. So these are all the square of the wave functions, which is the answer from the wave equations made by Schrödinger. So that's it in chapter 5.4.